Okay, so looking here, we're starting at 30, we're going to 50, so that's 20 meters. That's our distance. We're doing distance, not displacement here, between 0 and 2 seconds. From 0 to 4 seconds, I've already got my 20. Now I'm going to start here at 50. Okay, and I'm going to go to 4 seconds, which is down here. All right, so here we're looking at a position of 4 meters. Okay, so if I go 4 minus 50, I get negative 46 meters. So that means this section here, in terms of distance, is 46 meters long. So now my total distance to 4 seconds is 46 plus 20, 66 meters. All right, and then to 11 seconds, okay, all right, so 11 seconds, I've got to do this section here, which goes from 4 down to negative 42, it looks like. Okay, so from 4 to negative 42 is another 46 meters. Yeah. Okay, unless my mental math is wrong, you guys can correct me if I'm wrong there. Okay, and then I've got to go from 42, negative 42, back up to 0, like that. That's easy. Okay, that's just 42 meters. All right, so now we've got to add all of those things together. So we've got 92, 134, 140, or 154 meters in total. Okay, that sort of makes sense. It's just piece by piece and then add them all up at the end. All right, any other ones we need to go over? All right, so that's going to be kind of position versus time graphs. Remember that for reading positions at a given time, okay, we find that time on the x-axis, we go up, then we go over and find its value. In this case, it was positive 4. Okay, that's how we read that graph, and we get all those things off of it, okay, like displacement, okay, using final position minus initial position. Okay, we get velocity using final position minus initial position divided by time. Okay, and we get speed using distance over time, and that distance is, okay, piecemeal, final position minus initial position for all the different sections, and then just adding them together, okay? And then, of course, that acceleration thing that I missed, okay? Are there any curves on this graph? Then there's no acceleration anywhere on this graph. Every part of this graph is an object traveling at a constant velocity. All right, let's talk about the velocity versus time graph. All right, so I've got this velocity versus time graph. Okay, now, quick review. What can I read directly off this graph without doing anything but look at it? What's on this graph, guys? Velocity and time. Those are the two things I can read off of this graph. Looking at this graph, I can find out how fast and in what direction an object is going at any given time between 0 and 25 seconds. Okay? That's what I can read directly off this graph. I can also interpret directly off this graph what kind of motion is occurring without having to do any calculating. So, for example, here between 0 and 3 seconds, what is that object doing? It's accelerating. Yeah, it's going faster. It's accelerating in a positive direction. Absolutely. What's it doing in the 3 seconds after that? It's moving at a constant velocity of positive 12 meters per second. Okay, those are the kind of interpretation things I might ask off of this graph. Okay, and guys, I have very often asked a question like this. What is the acceleration between 3 and 6 seconds? 0, yeah. We just said it was moving at a constant velocity of 12 meters per second between 3 and 6 seconds. That means it's not accelerating. Okay? If there's no change in velocity, that's what acceleration is, then there's no acceleration. Anywhere I see a horizontal line on this graph, okay, the object is not accelerating. Okay. So, same as on the other graph, I can read how fast the object is going and in what direction directly off the graph. So, if, for example, they wanted to know what is the velocity of the object at 5 seconds. So here's 5 seconds. I go up and find the line, I come over, okay, its velocity is positive 12 meters per second. That's how I read that off the graph. Okay. Other things the graph might ask, okay, it might ask for acceleration. Okay, well, acceleration is the change in velocity divided by time. Can I read velocity off the graph? Can I read time off the graph? So this is just a matter of reading numbers off the graph and plugging them into that formula. Okay, very simple. So if they wanted to know what's the acceleration between 0 and 3 seconds, okay, well, at time 0, the speed appears to be 3 meters per second. That would be my initial. Okay, and at the end, at 3 seconds, it appears to be positive 12 meters per second. So I would have 12 minus 3, okay, divided by 3. That's going to be 9 divided by 3. So that's going to be 3 meters per second squared, and that would be positive. Okay, it's as simple as that. For calculating acceleration, you just plug the numbers in that you can read directly off the graph. Okay, now, another thing that this kind of graph might ask, okay, it might ask, what's the displacement between 0 and 6 seconds? Okay, now, there are a couple of ways that I can calculate displacement that we've learned in class. Okay, I can use this. Is that going to work on this graph? Nope. Position is not on this graph. I cannot get those values off of this graph. That formula is out. Okay, I also have this one. Okay, can I get that one? Can I use that? I absolutely can. Okay, I just have to manipulate it. So D equals average velocity times time. Okay, well, I can get average velocity off of this graph. Okay, average velocity is going to be halfway between the initial and final velocities. Okay, so on this graph then, in this first part, in the first 3 seconds, the object accelerates. Okay, it accelerates from 3 to 12 meters per second. So its average velocity would be halfway in between, right? Or the height of the triangle divided by 2. All right. Now, I also have to take into account that the object was initially traveling at 3 meters per second. So I also have to add on to that how far it would travel if it just kept doing that. Okay, that's also part of how far it goes while it's accelerating. Okay, so I'm going to have then these two shapes. So for this triangle, okay, it has a base of 3. The time is the base, so 3 seconds on the bottom, and it changes its velocity by from 3 seconds or from 3 meters per second to 12. So the height is 9. Okay, and then I would go 3 times 9, okay, which is 27 divided by 2. So during the acceleration part, it travels 13.5 meters per second. And then this box, this rectangle here, is 3 high by 3 on the base, so it's 9. Why am I putting positives beside it? It's displacement. It's a vector, and this object is moving forwards according to the graph, so I need to indicate these are forward displacements. All right, and then I've got, just going to erase this line here so we don't get confused because we're going to 6 seconds. Okay, after that, okay, between 3 and 6 seconds, the object travels at a constant velocity of positive 12. Does that mean its average velocity is also positive 12? Okay, it's not changing its velocity, so its average velocity is 12. Okay, so 12 times 3 seconds is positive 36 meters. This is the whole shape thing, okay, on this graph. We're using average velocity, we're multiplying it by time. It works out to, I calculate the areas of all the shapes and do a whole bunch of grade 8 geometry. Okay? All right, so what do I have to do with these 3 numbers now? Add them up, yeah. If I want the total displacement, I just did all this work. I should add them all together. That's going to tell me how far and in what direction, displacement, the object has covered. Okay, so 36 plus 13 and a half is 49 and a half, plus 9 is 58 and a half. Okay, so that's all of those added together. Okay, everybody all right with that? Okay, now, how would this change if I was talking about some of these parts of the graph where it's going backwards? Would I still calculate areas? I would. Those areas are now just negative, as long as I'm calculating displacement. What if I'm calculating distance? Everything's positive. Except I don't write positive beside it. I just treat it like it's all positive and add it all up because it's how far I go. Okay? I don't have to subtract that I came backwards. Everyone all right with that? Okay, another thing that this graph might ask for, it's a weird one, we haven't done it yet. But let's say after I did all of this, the question was, what's the average velocity between 0 and 6 seconds? Do I have a formula on the board that calculates average velocity? Have I just done all the work for that? I just calculated the displacement between 0 and 6 seconds, 58.5. Oops. Now it's displacement, positive 58.5. Okay, and that took 6 seconds. What do I do with those two numbers? Just divide them. Yeah, just plug them into this formula. That's the recognition that we have to get to when we're dealing with graphs. What am I getting off of this graph? What have I already calculated off of this graph? Do I have another formula that I can use that's on my formula sheet that has the information in it that I have? Okay, that's the process you have to go through. So if you don't have your formula sheet out and beside you at basically all times during this unit, you should. Okay, my physics 20s, they go through those formula sheets like crazy. Okay, they just get tattered because they're always out. Okay, they're always there on their desk because you're always having to refer back to those formulas. Okay. Yeah, that's on the back of the periodic table. So just, if you have your periodic table, that's where they are. Okay, so if I wanted to calculate, we already calculated average velocity. What if I wanted to calculate average speed? Would that be any different? Would just be, instead of displacement, it would be distance divided by time. So if I was doing any of the negatives, I would not treat them as negatives and then just go total distance divided by total time. Okay, ringing a bell? It just takes practice, guys. Here's kind of the commitment I'm going to need from you if you want to do well in this unit. Okay, the commitment is practice. Right? There's way more stuff in the workbook than we ever have time to do, except graphical. But that's why I'm giving you more. Okay, we're going to go through more tomorrow. Okay, but I need you to practice that stuff. The more you practice it, the better at it you'll get. Okay, here's the other commitment I need you to make. If you're struggling with this, come and see me for help. Okay, nothing is worse than going, oh, I really don't get this. It's so frustrating. Doing nothing about it, and then you're looking at a unit exam in front of you and going, I really don't know how to do this. I'm really screwed. Okay, I don't want that for you. That's awful. Okay, I can help you, but you got to come in. Okay, that commitment, that part's on you. Okay, I have no life. I'm here all the time. Okay, you can come see me before school, schedule help, lunch, after school. Okay, that's my commitment. Okay, your commitment is if you need it, come and get it. Okay, come and get that help. There is no shame in that. Okay. All right, here's what I want you to do. Those questions there, it says question 8, but it's actually, I think, question 9 in your booklet. Okay, answer those questions using this graph. Okay, I'm going to leave those numbers up there because you probably need them at some point along the way and save you calculating them again. Okay. All right, so part A on this one wants the displacement over the whole trip. So we've already got part of that done, but that means we have to do the rest of the shapes because, again, the shapes represent us using average velocity multiplied by time. Okay, so that means I'm going to continue this rectangle on over to here. Okay, I'm going to have a triangle on top of that rectangle. I'm going to have this big triangle here. Then I'm going to have this triangle right here. Okay, and then because that changes there, I'm going to have a triangle and a rectangle, and then I'm going to have this itty bitty triangle there at the end. Okay, those are going to be my shapes. So now I've got to calculate the areas of those. This one is 12 high and it's 4 wide. That's nice, that's 48. Okay, so positive 48 meters. This triangle here goes from positive 12 to positive 28. So it's 16 high by 4 wide. Okay, so 16 by 4. 64, okay, and then divide that by 2, so that one's going to be 32 meters. And then I've got this triangle here that's 28 high by 3.5 wide. That's the trick with that one. It does cut that time interval directly in half. Okay, so I'm going to have 28 by 3.5, and then divide that by 2, so 49. Okay, so that triangle there is positive 49 meters. And then I've got all of these little ones down here, as long as I remember that they're negative. So this one has a base of 1.5, okay, and it has a height of negative 12. So negative 12 times 1.5 is negative 18, divided by 2 is negative 9 meters. Okay, this triangle here goes from negative 2 to negative 12, so it's 10 high, and it's 1, 2, 3, 4, 5. So 10 times 5 is 50, divided by 2, that's negative 25 meters. Okay, this little rectangle here is 5 wide by negative 2 high, so it's negative 10 meters. And then this little itty bitty triangle here is 2 seconds on the base by negative 2 high. Negative 2 times 2 is negative 4, divided by 2 is negative 2 meters. All right, now I've got all of the shapes. Okay, that's like the rigorous part of this. Now, what do I do with all these numbers to get the total displacement? I add them all up, making sure that I keep the negative numbers negative. All right, so if I'm going about that here, so we have, we already figured out the 58.5 there for the first part, so we might as well use that. There's nowhere I can put, okay, there we go, put the calculator there. Okay, so we'll have our 58.5 plus 48 plus 32 plus 49 plus negative 9 plus negative 25 plus negative 10 plus negative 2. Okay, so the total displacement over the entire trip is positive 141.5 meters. Okay, that makes sense. This object was going forwards a lot more than it was going backwards on that graph, so it should end up ahead of where it started. Levi, you're giving it a crooked look. What's up? There's a lot of shapes. It's pretty easy to make one little mistake somewhere in there. Okay, but if you generally had this idea, if you messed up one number in there, okay, I mean, it's not the end of the world. I'm not going to give you one big like this on the unit exam. It'd be a bit simpler than that. Okay. All right, average velocity over the whole trip. Did I just do all the work for that basically? I did. Okay, and as long as I can remember that I have a formula that calculates average velocity, I can use the number I just calculated, 141.5 meters, and divide it by the total time, 22 seconds. All right, so 6.4, and that'll be positive, meters per second. Okay, questions on what I did there? Right, just use the formula that I had that had the things I had. Okay. All right, acceleration between 10 and 15 seconds. All right, so if I'm going to calculate acceleration, that's this formula here. Okay, at 15 seconds, the final velocity is -12. Okay, so we'll have -12 minus our initial velocity, 28. All right, so, and that's going to be over 5 seconds. So that's going to be -40 meters divided by 5 seconds. That's going to be -8 meters per second. Sorry, that's meters per second on top. Meters per second squared. Okay, for our acceleration during that period of time. Okay, acceleration between 6 and 10 seconds, same formula. Okay, my final velocity at 10 seconds is +28. My initial was 12. Okay, so 28 minus 12, okay, divided by, there's 4 seconds between 6 and 10. That's going to be 16 over 4, so +4 meters per second squared will be our answer for D. Okay, distance traveled between 0 and 10 seconds. Did I already do basically all the work for that? Okay, I just have to add all those numbers together. Okay, so back to, I'm going to take my 58.5. And I'm going to add on the 48 and the 32, so that's 8 plus another 80. Okay, it would be 138.5 meters for that one. Okay, and average speed between 10 and 20 seconds. Okay, so between 10 and 20 seconds, I'll use these two numbers here. Okay, and these ones here as well. So 58. 68, 88, 93 meters, okay, in that time. Okay, is the total distance. 93 divided by 10 is 9.3, okay, 9.3 meters per second for that one. That was just total distance over total time. And then acceleration between 13.5, that's right here, and 22 seconds. This is an easy one. What's the acceleration between 13.5 and 22? 0. Vf is 0, Vi is 0. 0 divided by anything is 0. Okay, so that one ends up being 0. All right. Before the bell goes, I'm going to hand out the handouts for tomorrow. Okay, I will post a practice quiz. It won't have a solutions video. I'll just post the answers. Okay, because I'm still making up the practice quiz and the real quiz because I ran out of graphic quizzes already. So I'm going to have to make up another one, which is no problem. Okay, it's just not going to have a solutions video for it. Okay, so let me hand out those packages here, and then we'll get going.